Well, like Miranda said, my name is Joost van Eyenoord, and as you can probably see right now, I work for AR Benelux, and I'm going to give a presentation about mixers, and more or less what is the difference between the different topologies of all the mixers, and which one should you choose in which situation, although that might be a little bit high level. So I would zoom in if there are any questions, but if there's more, just ask me. And I figured that you can ask me some questions surrounding the chat, which I could see here nice on the screen. So if any questions, just ask. And a little bit of the background where I got my information. We distribute a company called L3 Harris Narda Mytech. They make RF and microwave mixers up to 60 gigahertz, more or less. And if you look on the screen itself, you could see that the company AR Benelux has different fields in which they distribute. So in the EMC RF microwave field is where I'm working, SATCOM as well, and then some of my colleagues do something with AC/DC power, oscilloscopes, electrical safety, and in the end also test and measurement. Although test and measurement you could also scopes in, but that's our setup as a company. But let's proceed to how to choose the correct mixer. Now, what is a mixer at first? Usually a mixer in any given schematic, it would be given as it is here with 2 inputs and 1 output. So it's a 3-port electronic circuit. It's a non-linear circuit. Usually it has 2 inputs, and that can either be RF or LO, or it can be IF and LO. The definition of a mixer, well, you can read that on the screen yourself. The purpose of a mixer is in microwave system is to translate a certain frequency to another frequency. So that can either be translating a higher frequency to an intermediate frequency, or translating that same intermediate frequency to a higher frequency band. As you can see below, there are different schematics about it, but usually nowadays they use a hybrid at the LO and RF input, and then some sort of non-linear circuit that can either be Schottky diodes or it can be FETs. Filter it and put it on the output. So what do we see? How does a mixer work? What do we do? An LO. The LO stands for local oscillator. Usually this is just a local source used to upconvert or downconvert your frequency path. RF stands for radio frequency, of course, most of you would know. For the receiver, this would be the RF signal coming in. For a transmitter, this would be the output. It's the frequency that you want to transpose to another frequency domain. So you either want to get into RF, or you want your RF to get to your intermediate frequency. Well, and last but not least, then the intermediate frequency. That's usually the low frequency, can also be rather wideband, but that depends on the situation. So how does a mixer work? Well, depending on which way we go, you use the LO to drive a certain nonlinear circuit. That LO is also fed with RF, and then you will get the mixing components. The mixing components might either be the IF at the low part, or if you transmit IF to the upper part, it transmits. What does it do? LO and RF are added and subtracted. That's the most basic thing. A lot of more components will add, but usually those are filtered out, or the circuits inside prohibit them from reaching the output as well. But you get your LO plus RF and you get your LO minus RF. So in this case, if you subtract the LO from the RF, you get the IF. Where are they used? Well, the most common one and most frequently used is, for instance, your radio in your car receiver. You will have RF coming in at a certain band, either 3FM or Slam FM or Romantic FM, whatever you want or prefer. And with your local oscillator, you can tune that frequency to a fixed IF intermediate frequency, which you then present to your radio, or you demodulate the signal, and usually FM or AM. You demodulate that, and then you go to the output, and you get music out of your car. Another part might be, and I think some of the presentations this week will give some of the overviews, is a spectrum analyzer. Looking at a spectrum analyzer, in this case, you usually have two mixer circuits, which translate into your video bandwidth and your resolution bandwidth. A typical use of mixers can also be up converters and down converters in the SATCOM industry. So, looking at SATCOM, if you look at a down converter, it can either be from microwave down converted to L bands or any other, and then transmitted over fiber to a demodulator. And in that demodulator, you will have a mixer circuit again, or you have an up converter, which you have downstairs, where you up convert it to a certain SATCOM band and you want to transmit it. It goes the other way around, of course. So what kinds of mixers are there? A lot, and these are definitely not all. Most of the mixers you would see here, well, I start with a single FET mixer, SFM, but usually the most simple one is the second one, the single balanced mixer, which uses Schottky diodes, dual balanced, triple balanced, and then termination insensitive mixers. That's a slightly special one, but all of those are can be used in the same surroundings. Then we get to an image rejection mixer or modulator. Later on, I will talk about that a little bit more. A quadrature IF mixer, subharmonic mixer, sampling mixers, and then last but not least, and a strange one, slightly strange one, is the multiplier. Single balance mixer. A single balance mixer, you see two schematics of that. The most simple one is this top one with the hybrid on top. That hybrid makes sure that there is a rejection of your LO in the RF fields that gives your even harmonics no chance, basically. It's the simplest one we have, with a single balance bridge in between, which well, in this case, consists of Schottky diodes. It's the simplest one, economical, easy to bias, and the even RF products are cancelled out. Now, normally the third modulations are still in, so you have to do some filtering in front or beyond. The main disadvantage or problem with this one is that the IF cannot overlap with the RF. A double balance mixer makes it slightly more interesting. A double balance mixer uses balloons at its LO and its RF input, and the IF is fed somewhere in between the balloons of your RF. This can go up to a much wider bandwidth. And a second advantage, according to the single balance mixer, is that it has a better port isolation. The disadvantage, however, is that you need about 3 dB more LO power. Now, is LO usually not the biggest problem in circuits, so that should not raise the biggest problem. And the other part is that you have a limitation in your IF bandwidth due to the way it's set up. I talked about FET and I talked about Schottky diodes. I make a remark now at this presentation at the below point. If you use FETs instead of diodes, and it doesn't matter whether you do that in the single balance one, the double balance one, or any other you will see in this presentation, a FET instead of diodes gives you a little bit more of a better dynamic range. It gives you a better P1 dB performance, so you will have the possibility of a higher output or input, and you got a much higher third point interception point. So depending on the situation you're in, that could be of interest of. And then, well, to step it up again, we go to a triple balanced mixer, also sometimes called a double balanced mixer, because you use two of the same circuits of a double mixer. So I would say it is quadruple then in that case, but okay. They call that triple balanced. This again, this does allow you to have a much higher IF frequency. It could overlap with your LO and your RF frequencies instead of it should be in a different band. You have the possibility of a high bandwidth of IF, typically between half a gigahertz to 10 gigahertz. However, it's not possible to get to DC in this case. So in some situations, you want your mixer to work from DC to somewhere. That it doesn't do. The isolation between the different ports is much, much higher as well. Typically, you'll be around a 30 dBm of isolation with between the LO, the RF, and the LO and IF, which comes to the fact that you also have a better spurious performance. And again, the P1 dB and the third order intercept point are better. However, well, like I said, there's no DC IF possible, and again, you need about 3 dB more of LO power. Then the last one, which is a bit strange, but it's still in the same match as it is for all the other ones. Termination Insensitive Mixer. A mixer is inherent a non-linear device, which means that if you put a signal at the entrance, either the LO, the RF, or the IF, doesn't really matter, it will have a rather high VSWR, depending on frequency as well. That means power is reflected back into the circuit where it came from. And in some cases, that is not really wanted. So you would like that mixer circuit to be matched with its surrounding circuits. Then in that case, you could use a termination insensitive mixer. Anything it's connected to this will see 50 ohms of, or another one, but usually that would be 50 ohms of impedance at the LO and the RF side. Why? It's not that the VSWR is much better, although it is slightly, but it means that all the reflections coming from the nonlinear circuit of your mixer will be reflected back into the hybrid, and that hybrid will then reflect that into a termination. So that signal will not be reflected back into the inputs or the outputs. In this case, the surrounding circuit has the feeling that it will always transmit into a matched circuit. So that's a rather big advantage, especially if you're in communications. However, it's rather difficult to make. So at the moment, that is rather limited in bandwidth, although there are TIM mixers available up till about 18 gigahertz at the moment. Image rejection mixers. Now we get into a different field. So a slightly different setup, slightly different way of working. Normal mixers, a little bit of the background. Normal, if you have an LO and you have your RF, you could represent it like this at this point with a lower sideband and an upper sideband. And if you then mix that down, that frequency down with your LO to your IF, you will get both of them in your IF signal. So your low sideband and your upper sideband will both be there. If you don't want that, you can use an image rejection mixer. What does that do? Depending on how you set it up or which one you choose, it will cancel out one of the sidebands. So in this case, as it's shown here, it will only let through the upper sideband into your IF. Or if you choose differently, you can use it to only get your lower sideband into your RF. So this is neatly, if you don't want to mix that down or you don't want to filter that out at a later stage, or if it's impossible, you can use an image rejection mixer that will cancel out or at least suppress that second image to a certain amount of power. Then we get to the one part where it says image rejection modulator. Sometimes instead of mixer, the manufacturer will use the naming modulator. And in this case, that means it is going to up convert your signal. So it's IF towards RF. Why do they make the difference? Why do they make this? The naming difference in this case is that a modulator cannot be used the other way around. Most of the mixers, if you put RF in and you use your LO, you get your IF out. So if you put IF on that same mixer and LO, you will get RF out. So it can work both ways. For a modulator, that's not true. A modulator can only be used to up convert, and the other way around, in that case, a demodulator or mixer, they will call that. It will mean that you have it can only be used one way. Another more common mixer used nowadays is subharmonic or harmonic mixer. The advantage of an harmonic mixer is that the thing you do is that instead of using the LO as an LO signal at the first harmonic or your signal as LO, you can use the most common one is the half LO mixer. That basically means you put an LO in from 1 gigahertz. Internally, that will be multiplied, and the mixer will work with 2 gigahertz as an LO. So you need a lower source to do the same thing. Subharmonic, which was between the brackets, it basically means you can choose a mixer that uses anything else than the second harmonic, for instance, and you can have a third, a fourth, a fifth, and depending on the branch and the situation, you can go up to very high frequencies without using a very high frequency LO. So how does that work? Well, here's a slight representation of it upstairs. You see that the LO divided by N, depending on what you do, is fed to the system. There's a multiplier system or any other way to get harmonics in it. That harmonic is mostly or usually it's filtered going into the mixer circuit itself. And then out of that means if you use a 1 gigahertz LO inside the circuit, it will be translated to 2 gigahertz. And well, I think most of you will get the picture now. So what are the advantages? There are certain advantages to using harmonic mixing. Of course, the fact that you can use a rather cheap local oscillator. That local oscillator usually is depending on the higher frequency, but if you go into the millimeter wave or the high microwave frequencies, the higher the frequency, the more expensive your source will be. In this case, you would be able to use an LO at half of that frequency or even less. The The second advantage of such a system is that you will get a very high rejection of your LO signal in your RF. Typically, it's minus 55, minus 60 dB. So it's almost twice as good as a normal mixer. If you look at the rejection of your unwanted LO signal in your RF signal. Of course, there are some disadvantages as well. It will have a higher conversion loss. So the loss you will see from going from IF to RF or from RF to IF means you will add another 2 dB. It will have a higher phase noise. In case of a half LO, that basically means your phase noise in the end will be twice as big because of the translation of your LO to a higher frequency plane. And again, you need much more LO power due to the fact that the power from your harmonics will be less. And usually those mixers have poor PNDB or third order intercept figures. Another strange one, a sampling mixer. I'm not going into it but I'm only showing it. The sampling mixer in this case uses a sort of switching circuit, as you could see below left. Your RF is fed into that switching circuit. You use an LO and a Schottky diode to only use one of the sides of your LO. So either the positive, usually the positive side, and the other one is not. And that will switch open your FET at the speed of your LO. And then with some circuit behind it, it would mean you would translate your RF input into a certain DC IF output component. These mixers are mainly used, or at least what I could find about it is that they are used in phase loops, where you put such a mixer in your loop system to quickly be able to reach your unknown frequency on which you want to lock. So it's a way to speed up your PLL system or your PLL loop. Multipliers, although they're not in the same sense as a mixer, it will not translate a frequency into just one or several frequency components. What it will do is you put in one frequency and it will translate that into a higher harmonic. So the output of a multiplier, depending on which one you choose, you can choose one who does only ×2. So that means your RF in and your RF out will be ×2. And I see there's a little mistake, but your RF in the ×2 will, as it says, will be twice as high. You can use a third order multiplier as well, where you go to the third harmonic. There is a strange brand in this case as well. That's a comp generator or a multiplier. You put one RF source in, and the output will be an evenly distributed RF out of several harmonics compared to the one you put in. Comp generators are, for instance, used in EMC chambers to determine their spread of frequency. You put a comp generator in your room, and you try to measure and to see how it's evenly spread in your room. But there are multiple options to use such a system. How do we determine whether we need the correct mixer? Well, of course, we have to ask ourselves, in what kind of background are we going to use this? Either communication, radar, is it electrical warfare? Will we use it in test equipment? Will it be space used, or any other part where we want to use a mixer? So we have to ask ourselves, for what purpose do we need this? Then we have to look at the specifications. What are the most important specifications of a mixer? Well, of course, in what frequency range do we want to work? And what frequency do we want to translate? What power do we put into the mixer and we expect to get out of the mixer? So what's my 1 dB compression point? The conversion loss, which conversion loss do we want, or which is preferable? And usually a mixer has a rather high conversion loss. It will add noise. Anything put in a stream will add noise to a system. It differs from which one you use. Well, what kind of VSWR do we want? Is it permissible to have a 1 to 2 or one, whatever part of it? In case you have an active mixer, which is possible, for instance, if you put an LNA in the same system to combine it, which kind of DC supply can I permit myself? What is the system willing to put on this? Looking into that, and of course, well, as always, you will have a certain budget. Some solutions are more expensive than the other one. That's the way life is. So if you fill this in for yourself, you can narrow it down already. If you go to radar, what are the key mixer characteristics if you use radar? Usually, well, high performance, dynamic range, because you send out a signal and you're going to look at a much lower range coming back. So you want it to be low loss, low phase noise, because you're gonna usually radar work with comparing the phase. So you want not that much phase added to your system, and you don't want unwanted signals coming in there as well. So your spurious signals should be low. Usually image rejection is a good thing. Higher integration, depending on the radar and how big you want it to be, you can either use plug-in, but you can also put, you can make it on a circuit board. Do we want filters in it, depending on the bandwidth, depending on the frequency used? And sometimes amplitude and phase matched channels should be there as well. But that also means that your mixer should be phase matched. So questions to ask yourself and then narrow down the ones you can use. Going to communications. Well, usually going into SATCOM or into communication bands, it means the bandwidth is not that high. You got multiple bands, but either you work in C band or you work in KU band or you work in whatever band you want. It is a determined bandwidth, which is not overstating multiple octave frequencies. Depending on the situation, we see nice military subjects, so money might be a little different at the point. But surface mount, drop-in designs, low phase noise are usually the specs asked for communications. Which mixers do we need? Well, we can use double balance mixers we'll have a high isolation. The availability is that they are available in surface mount designs, but and drop-in designs as well. You can design one yourself depending on where you are. And then depending on the frequency you want to use, subharmonic mixing might be of interest as well. And in some cases where you have multiple tuner passband filters, there we go. There's the multiplier series where you could use a multiplier or a comp generator and just filter or switch between the different LOs in this case quite quickly. And that means you can tune quite neatly to a certain channel. Well, electronic warfare, not much going on there. But key mixer characteristics might be you want it to be wideband, low spurious, high performance modulator as well, depending on what part of the electronic warfare there is. But for sure, all of the mixers on the right might be available for that. I'm not going to mention them all, depending on what you want to do. But one thing at the bottom usually is high carrier rejection. Well, that might determine already which kind of frequency or which kind of mixer you want to add to your list. Test equipment. Well, we have a lot of test equipment, and probably some of the presentations will get into this topic. But usually, if you go to a spectrum analyzer is pretty wideband. Multi-octave works from, most of them works from 9 kilohertz to way beyond the gigahertz versions. So you want your mixer to be very wideband. You want them to be low phase noise because you want to measure that. Well, as I've shown in one of the previous slides, usually you have multiple mixer stages depending on the brand and the topic. But yes, it will get into the higher bandwidth versions. And of course, you make a lot of them, so you want them to be low cost. And in the end, space qualified. The one thing I want to say about space qualified is that any of the above may apply. So all of the mixer setups and all of the things that I've talked about can apply on a space qualified system. The only main difference then, besides the fact that it usually becomes more expensive, is that they're going to follow different protocols. So if you want one mixer in a system, most manufacturers will make several and then start testing them in several environments and to make them ready to work up into space. And all those protocols that are then in place to make sure that it will work up into space makes it more expensive. But all of the systems described above will be able to be used in space. And that comes to the end of my presentation for now. My name again is Joost van Heijenoord. I work at AR Benelux together with Hugo Landman. And I'm happy to answer all or one of the questions you would have. Got much more information on the background of this, but it was too much to get into this at a certain level. So if you want to know anything more about mixers,